chemistry, we often analyze samples of materials to determine their properties and composition. These analyses may be quantitative or qualitative in nature. While quantitative analysis measures how much of a substance there is, qualitative analysis establishes what that substance is. This video outlines the techniques involved in elementary qualitative analysis and the chemistry that underpins it. On completion of the qualitative analysis, which involves identifying the constituents of single substances or mixtures, you should be able to 1. Identify the cations, lead 2+, aluminum 3+, calcium 2+, zinc 2+, iron 3+, iron 2+, ammonium, and copper 2+ ions. 2. You should also be able to identify the gases, hydrogen, oxygen, carbon dioxide, ammonia, sulfur dioxide, chlorine, nitrogen dioxide, and water. 3. And you should be able to identify the anions, carbonate, sulfate, sulfite, nitrate, bromide, iodide, and chloride. Since most methods of qualitative analysis deal with ions, it is useful to keep in mind some of the properties of ions. 1. Ions can form insoluble compounds with other ions. 2. Their color or lack of color in solution or solid state is a fairly accurate indicator of the nature of the substance. Based upon this, if the compound is black, it is probably an oxide. If the solid or its solution in water is colored, this indicates that a transition metal ion is probably present. Iron 2+ solutions tend to be green, copper 2+ solutions are blue, and iron 3+ solutions are yellow. If the compound appears as a white solid and its aqueous solution colorless, this indicates that the transition metal ions are probably absent, the notable exception being zinc, whose compounds are colorless in solution and white as solids. So you see, looks can be deceiving. Appearance is not a 100% effective guide in determining the identity of a compound. The general method involves identifying metallic ions or cations based on the color and solubility of the hydroxide formed when they react with aqueous ammonia and aqueous sodium hydroxide. If this does not narrow down the unknown to a single cation, a confirmatory test will need to be done. The general method of analysis involves, firstly, preparing a solution of the solid under investigation. Next, place a sample of the solution in a test tube. Then, using a dropper, add sodium hydroxide solution dropwise to see if a precipitate forms. The next step involves adding excess sodium hydroxide solution to see if the precipitate dissolves. If no precipitate forms, warm gently and test for ammonia. To another portion of the solution, add aqueous ammonia drop by drop and look for precipitate. Again, add aqueous ammonia in excess to see if the precipitate dissolves. If required, carry out a confirmatory test on another portion of the solution. The metal cations form insoluble hydroxides with sodium hydroxide solution. The precipitates formed are colored as follows: copper 2 hydroxide, blue; iron 2 hydroxide, dirty green; iron 3 hydroxide, reddish brown. All other precipitates appear white. Calcium hydroxide, copper hydroxide, iron 2 and iron 3 hydroxide are basic and therefore do not react with excess sodium hydroxide. Precipitates remain. Aluminum hydroxide, zinc hydroxide, and lead 2 hydroxide are amphoteric. They react with acids and bases. They react with excess sodium hydroxide to form soluble salts, hence the precipitates appear to dissolve in excess sodium hydroxide. The metal hydroxides formed with aqueous ammonia are insoluble in excess except copper and zinc hydroxides, which dissolve in excess aqueous ammonia as soluble complex ions are formed. Aqueous ammonia will not precipitate calcium ions. Calcium hydroxide only precipitates when the concentration of hydroxide ions in solution is relatively high. As ammonia is a weak alkali, it has a relatively small amount of hydroxide ions in solution when compared to strong alkalis. The zinc ion is generally confirmed by the fact that its hydroxide is soluble in both excess aqueous ammonia and aqueous sodium hydroxide. To differentiate between aluminum 3+ and lead 2+ ions, solutions of iodide, chloride, or sulfate can be added. In all cases, lead 2 ions will form a precipitate while the aluminum ion will not. These precipitates are lead 2 chloride, white, lead iodide, yellow, and lead sulfate, white. The amphoteric hydroxides, aluminum hydroxide and lead hydroxides, and the basic hydroxides, iron 2 hydroxide and iron 3 hydroxide, do not react with excess ammonia solution. The precipitates remain. Zinc hydroxide and copper hydroxide react with excess ammonia solution, forming a colorless and a blue solution respectively. Precipitates disappear. The ammonium cation does not form an insoluble hydroxide, but on heating reacts with the hydroxide ion, forming ammonia and water. Ammonia gas turns damp red litmus blue as it is alkaline in nature. It also has a pungent odor and forms dense white fumes with hydrogen chloride gas. The conformation of the ammonia gas confirms the presence of the ammonium ion, NH4+. Moist litmus paper acts as a standard in testing for the presence of gases, though by itself it is not enough. Always remember to have your litmus paper and other gas testing reagents ready before the commencement of the test. Ensure litmus is damp and it, as well as any other test paper, is held above the test tube in the escaping gas, ensuring they do not touch the test tube. For the sulfur dioxide test, a strip of filter paper may be dipped into acidified potassium manganate or dichromate and held in the escaping gas. Given the density of carbon dioxide, it may be poured into the aqueous calcium hydroxide or the delivery tube used to bubble the test gas into the aqueous calcium hydroxide. Hydrogen, oxygen, and water are all colorless and odorless gases that have no effect on damp litmus paper. So how do we differentiate them? Hydrogen burns with a popping sound when a lit splint is inserted into it, while oxygen will relight a glowing splint. Carbon dioxide is also colorless and odorless, but will turn moist blue litmus paper to pale red. It forms a white powdery precipitate when bubbled through lime water that dissolves to form a colorless solution on continued bubbling of the gas through it. Sulfur dioxide, hydrogen chloride are colorless gases that turn moist blue litmus paper red. Ammonia has a pungent odor and forms dense white fumes when reacted with hydrogen chloride gas. Sulfur dioxide has a choking smell. It turns acidified potassium dichromate solution from orange to green and acidified potassium manganate solution from purple to colorless. Hydrogen chloride also has a pungent odor. It fumes in damp air and forms dense white fumes with ammonia gas. Nitrogen dioxide is red-brown and has an irritating smell. It turns moist blue litmus paper red. Chlorine is yellow-green and also has a choking smell. It turns moist blue litmus red and then bleaches it. Bromine is red-brown and has a choking smell and turns moist blue litmus paper red and bleaches it. Iodine has violet vapors and forms a black sublimate. It turns moist blue litmus paper red, then bleaches it. It is yellow, orange, or reddish-brown in solution. Non-metallic ions or anions are generally identified based on the evolution and identification of gases produced when the compounds are heated or reacted with acids. The color and solubility of precipitates formed on reaction with barium ions, silver ions, and lead ions are also used. The addition of the reagent silver nitrate followed by addition of ammonia solution is used to identify the halide ions. The chloride ion forms a white precipitate which is soluble in aqueous ammonia. The bromide ion forms a cream precipitate which is slightly soluble in aqueous ammonia and soluble in concentrated ammonia. And the iodide ion forms a yellow precipitate which is insoluble in aqueous ammonia. All silver halides decompose to silver when exposed to light. The silver appears as a black, sometimes colloidal precipitate. Barium ions are added to a solution to test for carbonate, sulfate, or sulfite ions. These ions give a white precipitate when they react with barium ions. Dilute acid is then added to the precipitates formed to differentiate which of the ions is present. The soluble barium salt and acid combination used for this test are barium chloride and dilute hydrochloric acid, or barium nitrate and dilute nitric acid. The sulfate ion does not react and is in fact insoluble in the dilute acid. This serves as the confirmatory test for the sulfate ion. The carbonate and sulfite ions will react with the acid and give off carbon dioxide and sulfur dioxide gases, respectively. If carbon dioxide is present, it will form a white precipitate if bubbled through lime water, calcium hydroxide. Sulfur dioxide will cause potassium dichromate paper to change from orange to green. Both gases are acidic and will turn damp blue litmus paper red. Lead-2 ions form a white precipitate with chloride, sulfate, sulfite, and carbonate. Lead-2 chloride is soluble in hot water and reprecipitates on cooling. Lead-2 sulfate is insoluble in dilute nitric acid. Lead-2 sulfite reacts with dilute nitric acid to form sulfur dioxide. Lead-2 carbonate reacts with dilute nitric acid to form carbon dioxide. Lead-2 ions form a cream precipitate which dissolves in hot water and reprecipitates on cooling with bromide ions, and a yellow precipitate with iodide ion which is sparingly soluble in hot water. To test for the nitrate ion, concentrated sulfuric acid and copper turnings are added to the sample and warmed gently. If nitrogen dioxide gas, which is brown in color, is evolved, it shows the presence of the nitrate ion. The resulting solution is generally blue due to the presence of the copper 2 ion. Another test for nitrate ions involves the addition of sodium hydroxide solution followed by aluminum powder to the test solution and warming gently. The formation of ammonia gas indicates the presence of the nitrate ion. The solid is to be heated gently at first, then strongly, until no further change is observed. The effects of the heat and the appearance of the residue after heating is to be noted. All escaping gases are to be tested. Some hydrated salts will tend to dissolve in their water of crystallization, forming a saturated solution which, on further heating, produces water vapor which sometimes condenses on the cooler part of the test tube and the solid reforms. The presence of the water could also mean the presence of a hydroxide, as they thermally decompose to produce water and the metal oxide. The evolution of iodine indicates the presence of an iodide. The evolution of bromine indicates the presence of a bromide. The evolution of ammonia indicates the presence of an ammonium salt. Oxygen by itself indicates the presence of a nitrate of a reactive metal, usually potassium and sodium. The nitrates of the group 1 elements thermally decompose to the metal nitrite and oxygen. Nitrogen dioxide accompanied by oxygen indicates the presence of a nitrate other than the metals of group 1. These nitrates of less reactive metals decompose to produce the metal oxide, nitrogen dioxide, and oxygen. The evolution of carbon dioxide indicates the presence of a carbonate other than sodium or potassium. These carbonates of less reactive metals thermally decompose to give the metal oxide and carbon dioxide. The evolution of sulfur dioxide indicates the presence of a sulfite. Metal sulfides thermally decompose to give the metal oxide and sulfur dioxide. A residue that is yellow when hot and white when cold indicates the presence of lead-2 oxide and could also indicate zinc ion. Blue or green solid given black residue could mean copper-2 ions, and pale yellow or green solid given brown residue could mean iron 3 or original iron 2 that was oxidized on heating to iron 3. A little dilute acid, usually hydrochloric acid, is added to the test substance, and if no reaction occurs in the cold, the mixture should be warmed gently. The evolution of carbon dioxide indicates the presence of a carbonate. The evolution of hydrogen indicates a metal above hydrogen in the reactivity series. The evolution of sulfur dioxide indicates the presence of a sulfite. A little concentrated acid, usually sulfuric acid, is added to the test solid or solution and warmed gently. The evolution of carbon dioxide indicates the presence of a carbonate. The evolution of hydrogen indicates a metal above hydrogen in the reactivity series. The evolution of sulfur dioxide indicates the presence of a sulfite. The evolution of hydrogen chloride indicates the presence of a chloride. The evolution of iodine indicates the presence of an iodide. The evolution of bromine indicates the presence of a bromide. The evolution of nitrogen dioxide indicates the presence of a nitrate. Carbonate. When heated, the solid decomposes and carbon dioxide is evolved. On addition of dilute hydrochloric or nitric acid, carbon dioxide and water are formed. Sulfates precipitate from solution as white barium sulfate on addition of a soluble barium salt, example, barium chloride. The precipitate is insoluble in dilute hydrochloric or nitric acid. Sulfide precipitates from solution as white barium sulfite on addition of soluble barium salt, example barium chloride. The precipitate reacts with dilute hydrochloric acid or nitric acid to produce sulfur dioxide. Nitrate. The solid decomposes with the evolution of nitrogen 4 oxide, and solution turns blue on addition of concentrated sulfuric acid and copper turnings. Ammonia is given off after the addition of aqueous sodium hydroxide and aluminum powder. Chloride. It precipitates from solution as white silver chloride on addition of silver nitrate solution. The precipitate is insoluble in dilute nitric acid and sulfuric acid, but soluble in dilute ammonia solution. The solid also decomposes with the evolution of hydrogen chloride gas when treated with concentrated sulfuric acid and warmed. Bromide. This precipitates from solution as pale yellow cream silver bromide on addition of silver nitrate solution. The precipitate in dilute nitric acid and sulfuric acid is slightly soluble but readily soluble in concentrated ammonia solution. The solid decomposes with evolution of bromine when treated with concentrated sulfuric acid and is warmed. Iodide. This precipitates from solution as yellow silver iodide on addition of silver nitrate solution. The precipitate is insoluble in dilute nitric and sulfuric acid and almost insoluble in concentrated ammonia solution. The solid decomposes with evolution of iodine when treated with concentrated sulfuric acid and is warmed.